Hey there, it's Shannon Matrick-Myers, and today we're looking at part of 8.3, non-homogeneous, sorry, there's an O here, my bad, homogeneous linear systems, and we're only going to cover the variation of parameters method due to lack of time and the fact that this is the more powerful method for solving non-homogeneous linear systems. So we want to find our particular solution, xp, in the equation x equals xc plus xp. Now, I know that the author of, Zill, the author of our text, bolds our matrices. I can't do that when I'm writing in formulas. So the capitals can be assumed to be matrices. Okay. All right. In the last couple sections, we learned that the general solution of a non-homogeneous linear system, x prime equal to a times x plus f. We'll put f at t just so that we know that there's that functions of t within that matrix on an interval I is x is equal to xc plus xp, where xc is equal to c1 times x1 plus c2 times x2. Again, these are all column vectors or matrices. And then you'd keep going, except for the constants. They are constants. All the way down to cn times xn. All right? And the way that we find all these things is via the methods in 8.2, all that good stuff, where we find the eigenvalues and the eigenvectors to find xc. So xc is the complementary function or general solution of the associated homogeneous linear system x prime equals a times x, and xp is any particular solution of the non-homogeneous system. We also saw how to obtain xc when the coefficient matrix A was an n by n matrix of constants. Now we will explore one method for obtaining xp, and that method is variation of parameters. Again, I made that decision based on the fact that this is the more powerful method. So first of all, in order to understand the variation of parameters, we're going to look at a fundamental matrix. So if x1, x2 all the way down to xn is a fundamental set of solutions of the homogeneous system, x prime is equal to a times x on an interval I, then its general solution on the interval is the linear combination x equals c1 x1 plus c2 x2 all the way down to adding c sub n xn. Or if you want to get a visual of this in terms of matrices, x would equal to c1 times the matrix x11, x21, all the way down to xn1. So these are all column matrices, plus C2 times x12, x22, all the way down to xn2. We would continue until we got to Cn times x1n, x2n, all the way down to xnn. And this in turn also equals to, if we write it in terms of one happy matrix, even though it's going to look very wide, it's really just one column. So it'll have n rows, one column, and we would just add each of these. So you would have your constant C1 times x11 plus C2 times x12. You'd go all the way down to Cn times x1n, and then the next entry on the next row would be C1 times x12, because we're in row 2 now. My bad, x21 plus C2 x22, all the way down to Cn x2n. Cool so far? And then, of course, these would all continue. So the last entry would be this sum, C1 xn1 plus C2 xn2, all the way down to Cn xnn. And that is what our general solution would be, x. Cool, cool? Okay, so the general solution from above can be written as the product x equals phi, this is another matrix, in terms of t, times c, which is a matrix, where c is an n by 1 column vector of arbitrary constants, C1, C2, all the way down to Cn, and the n by n matrix, whose columns consist of the entries of the solution vectors of the system, x prime is equal to a times x. All right, so now here we go. Here's kind of the meat of what's going on here. We end up with phi at t, the matrix phi at t is equal to x11, x12, all the way down to x1n, x21, x22, all the way down to x2n, and then this would continue until we got to xn1. This would continue till we got down to xn2, and then we would go over and down, and we'd be at the entry xnn. Groovy? And this is called a fundamental matrix of the system on the interval. Now, two properties of a fundamental matrix that we will use. A fundamental matrix phi at t is non-singular if phi at t is a fundamental matrix of the system x prime equals a times x, then it turns out that phi prime at t is equal to a times phi at t. If we look back at theorem 8.1.3, it's one part of the theorem, I think it's number 9, we're going to see that the determinant of phi at t is the same as the Wronskian, denoted W, at x1, these are all vectors, x2 all the way down to xn. Hence, the linear independence of the columns of phi at t on the interval I guarantees that the determinant of phi at t is non-zero for every t in the interval. And when that's non-zero, you know that there is a unique solution to the system. And so that tells you it's non-singular. So what else does non-singular tell us? Awesome, that we know that the matrix is invertible. That's why we needed that property. So this is the rationale for this first property. This second part is the rationale for the second property. So since phi at t is non-singular, the multiplicative inverse phi inverse at t exists for every t in the interval. Since every column of phi at t is a solution vector of x prime equals a times x, again, all matrices, the second property holds true. Okay? And because all right, now let's get into variation of parameters. So just a little bit of why does it work kind of thing, and then we will get to a couple of example problems, and then we'll be done. So variation of parameters, similar to the procedure in 4.6, we want to see if it's possible to replace the matrix of constants C from x equals phi at t times c by a column matrix of functions u at t equal to u1 at t, u2 at t, all the way down to un at t, so that the particular solution matrix xp is equal to phi at t times u at t. Now note that phi at t is n by n, u at t is n by 1, and so this multiplication is defined and results in an n by 1 matrix. So this xp is a particular solution of the non-homogeneous system x prime is equal to a times x plus f at t. Again, all of these are matrices. All right, so let's do it. We have x prime is equal to a times x plus f at t. We have xp is equal to phi at t times u at t. And we have x prime at P is equal to, using the product rule and making sure, because of the dimensions, that phi at T is always on the left side, we'll keep phi at T the same, and then we'll get u prime at T, and then plus phi prime at T times u at T. Good so far? Awesome. Note, I'm just repeating myself about the dimensions. Unlike differentiating functions, which are not entries in a matrix with the product rule, order is important here, since phi at T has size n by n and u at T has size n by 1. Phi at T must be first, as does phi prime at T. Now that we have that going on, let's take a look at this x prime at T. So we have x prime, at P, so the particular solution, the particular matrix of solutions. So this is going to be A times xp, I'll explain where I'm getting this in a minute, plus f at T. So we had x prime up here, we had x prime was equal to A times x plus f at T. So x prime of the particular solution would be A times x P plus f at T. Cool? So that's all that happened here. Now, replacing xp, we would have, and replacing x prime at P, we'll do two steps. So x prime at P from the third line is equal to phi at T times u prime at T plus phi prime at T times u at T. So x prime at P is equal to all of this. Groovy? All right, and then on the other side, we have A times xp, but what is xp? Xp is phi at T times u at T. So all I did here is I replaced xp with this expression here. And in the first one, I had done my x prime at P. Cool? Now I still have plus f at T hanging around. Don't forget about that one. Now let's just do a little bit of algebra. So here we go. Didn't we see somewhere up here that, here we go, phi prime at T was equal to A times phi at T. And so we have this here. So we're going to substitute in for phi prime at T. We'll substitute in A times phi at T. Okay, so this came from the fact that phi prime at T is equal to A times phi at T. And that's going to equal to A times phi at T times u at T plus f at t. Cool so far? All right, well, notice that if we subtracted, we have the same matrix here and here. And so if I added the opposite, to both sides of that matrix, I'd have the 0 matrix of that dimension, which I believe we said would be, I think it's going to be n by 1. Okay. And then, so that would just go away. It becomes a 0 matrix. When you add the 0 matrix to anything, you just get what you're adding to that 0 matrix. So we would end up with phi at t times u prime at t equals f at t. Now we know that the inverse exists for phi at t. And so we'll evaluate the inverse on the left side of each expression, and then we will get a result of the identity matrix. Well, the identity matrix times any matrix is that matrix. So we'll get u prime at t is equal to phi inverse at t times f at t. Cool so far? Isn't it kind of groovy how that works out? And then if you were to integrate both sides, right, you would end up having u at t is equal to the integral of phi inverse at t times f at t dt. Cool? Okay, so now let's check this out. Since xp equals phi at t times u at t, a particular solution of x prime equal to a x plus f at t is xp equals phi at t, times, well, n for u at t, we're going to put the integral of phi inverse at t times f at t dt. So our u at t was here, and so our xp, is phi at t times u at t, and so we would plug that in here. Cool? All right, and then finishing it up, we have the general solution, which, remember, was x equals xc plus xp, which gives us a result of x equals phi at t times c plus phi at t times the integral of phi inverse at t times f at t dt. Cool, cool? And so I don't know if that's really a proof. It's just really a, hey, this is where stuff comes from. All right, so at the end of the day, I just wrote it down here, basically the last two lines, so you'd have it in print. And let's take a look at an example. All right, so use variation of parameters to solve the non-homogeneous system. So here we go. We have dx dt is 2x minus y, and dy dt is 3x minus 2y plus 4t. So let's write down what all we know, right? So we know that a is equal to what? Beautiful. It's going to be 2, negative 1 going across, and then 3, negative 2. And we also have capital F at t is equal to 0 and 4, and then that's times t, right? Or you could just say 0 and 4t, bring in the t in. So step 1 is to find xc, right? So find xc by solving x prime equals a times x. So here we go. How do we do that? Well, we do the whole bit with the eigenvalues. So we want to find the determinant of a minus lambda I. Remember, I in this case will be the identity matrix for a 2 by 2, which is 1, 0, 0, 1. And so this will end up being the determinant of, so 2 minus lambda times 1 is 2 minus lambda. We'll just have our negative 1 the same, and 3 will be the same, and then do you see that we'll have negative 2 minus lambda in our determinant? So in general, if you have a determinant of some a, b, c, and d, that's equal to 1 over ad minus bc times the matrix. You've switched the diagonal entries, and then you put the opposite sign on the other one, not the on the off main diagonal ones. The main diagonal switches, and the other one you apply the opposite sign to. So it's easy enough to do that for this one. Now remember, we want to set this determinant equal to 0, so I'll start doing that. And then we will get 2 minus lambda. I'm going to factor out the negative and from the negative 2 minus lambda and write that as 2 plus lambda, just to clean it up a little. And then minus negative 3 when I multiply 3 and negative 1. So 0 will equal to negative quantity. We'll have 4 minus, it's a difference of squares, right? So the middle terms will zero out, and we'll have 4 minus lambda squared plus 3. And then this will give us positive lambda squared. And then negative 4 plus 3 is minus 1. And so lambda will equal to plus or minus 1. So let's say that lambda 1 is equal to negative 1, and lambda 2 is equal to positive 1. So we found the eigenvalues. So this section was eigenvalues. And then now we need to find eigenvectors, right? So eigenvectors, well, what you do here is, I mean, there's different ways you can look at this. To find the eigenvectors, you need to basically set your, so this is going to be for lambda 1 equal to negative 1. So the notation's different. If you're also taking linear algebra with us, the notation that this author uses is a little different, but it's okay. It's the same. You get the same result. So basically, what you want to do is you want to have your A minus lambda times I is equal to the 0 vector to find your eigenvalues. So, well, how do you do that? You would make a matrix, and then we'd be plugging in, we already have A minus lambda I inside our determinant, the entries for this matrix. So plugging in negative 1 for lambda, we'll have 2 minus negative 1, so we will get 3, and then negative 1 and 0, and then we'll have 3. Negative 1 minus a negative 1 will give us a negative 1 and 0. Cool so far? And so what does this mean? If you remember, you can, you know how to find the reduced, you don't even need reduced row echelon form. We just want to simplify this one. So basically what's going to happen is if you add the opposite, you'll end up getting an equivalent matrix of 3, negative 1, 0, 0, 0, 0, because you have the same line, right? And so what does that mean? That means that 3 times k1 minus k2 is equal to 0. 3k1 is equal to k2. So if we call our first eigenvector capital K1, right, and if we let K1 equal to 1, then K2 is going to be what? Beautiful, 3. So we just let small k1 equal to 1, and that gave us that K2 was 3. So that is what the eigenvector, an eigenvector could be, right? Now, let's think about what our matrix X1 would be. That's going to be C1 times this matrix we found, the column matrix, times E, and then you replace the lambda. Remember, you have e to the lambda t, that's from another section. Well, we replace lambda with negative 1. So we'll have negative 1 times t, which of course is e to the negative t. I'll keep the negative 1 in there for now. And we got that one from right here because our lambda 1 was negative 1. Groovy? Okay, so next eigenvector, you do the same thing, except we have our next eigenvector. So we're going to cruise on up here, and then we're going to look at lambda 2, which was equal to positive 1. And so again, we're solving that A minus lambda I equals 0. In this case, lambda is 1. And so the a minus 1 times I, you just plug in the 1 where you see the lambdas in there. And so 2 minus 1 is 1. We'll have the negative 1 hanging out. We'll have a 0 because that's equal to that 0 vector. And then we'll have 3. Negative 2 minus 1 is negative 3. And then we have our 0. Well, that is equivalent to, if we multiplied the first row by negative 3 and added, we'd have our same first row, and this one would 0 out. So if you think of it as K1 equals 1, I'm sorry, let's do it like this. Just putting it back in terms of a system and writing the system in terms of K sub 1, K sub 2. We would have 1 K1 minus 1 K2 is 0. So that means that K1 equals K2. If we let K1 equal to 1, that would also equal K2. So the eigenvector K2 would equal to 1, 1, or an eigenvector, right? Because you could let K1 equal whatever you want. But might as well just keep it easy, right? 1, 1. And then that means that X2 has to be C2 times 1, 1 times E. This time our eigenvalue was 1, so we would get e to the positive t. So again, we have that's where we got this 1. And we were plugging 1 in here. And that's where we got those values. Cool, cool? All right, so now we've done that part. Isn't that exciting? So what have we found? We have found that XC equals C1 times 1, 3, and that was times e to the negative t, and then plus C2 times the 1, 1 column vector or column matrix, e to the positive t. Groovy? All right, so step 2 is we want to find XP. All right, so sorry about the siren. So this is the new stuff, all right? So remember that XP is equal to theta at t, these are all matrices, times the integral of theta inverse at t times capital F at t dt. Cool, cool? All right, so we need to find all this good stuff. All right, ready? First off, we need to find phi at t. Okay, so to find phi at t, super easy. We just assume, you know, C1 and C2 to equal to 1, and then we bring these expressions into one happy matrix. So phi at t is equal to 1 times e to the negative t is e to the negative t. 3 times e to the negative t is 3e to the negative t. And then the other ones will just be e to the t, because they had a coefficient of 1. All right. Now we need to find phi inverse at t. And that one, we're going to use this method here again. Okay, so with this stuff here. So we're going to get 1 over e to the negative t times e to the t minus e to the t times 3 e to the negative t as the coefficient, and then times the matrix. We'll switch the main diagonal entries, so e to the positive t will be on the top left, e to the negative t bottom right, and then we change the coefficient signs on the other two. So we'll have a negative e to the t and then a negative 3e to the negative t. Groovy? Almost there. All right. Now we also already have f at t, don't we? So now we just are going to want to be simplifying our phi inverse at t. So here we go. This is going to be phi inverse at t equals e to the negative t times e to the t. Remember, you just add the exponents. That would be e to the 0. So we would just get 1. So we'll have 1 over 1 minus 3. So that will be negative 1/2 times all of these. And so we will end up with, let's see if we need to bring that in. I don't think we really need to, because we're going to be using phi inverse here. So we could just factor out that negative 1/2. I don't see any problem with that, because it's just a constant. So I'm going to keep it written like this. All right, so now let's find xp, all right, because we know f at t from above, right? The vector, column vector 0, 4 times t. So here we go. Coming down to our next page, we have xp equals phi at t times the integral of phi inverse at t times capital F at t dt. So here we go. Let's go ahead, so we don't have to keep writing out phi at t in that matrix format. Let's find some parts of this. So we can certainly find phi inverse at t times f at t, because we have to do that before we integrate. So here we go. So we have phi first, and remember, we're going to factor out a negative 1/2. So that's going to go along for the ride the whole time. We'll just put our e to the t, negative 3e to the negative t, negative e to the t, and e to the negative t. We have 0, and we have, I'm going to write it as 4t. And then I'm just multiplying e to the t times 0 is 0, plus negative e to the t times 4t is going to give me negative 4t e to the t. And that's our first entry. And negative 3e to the negative t times 0 is 0, and then we add e to the negative t times 4t. So we'll get a positive 4t e to the negative t. Now, do you see that we could factor out a 4 from this? And we'll just have te to the t, a negative in front of it, and then a positive te to the negative t. So now I'm going to come up here and put 4 over 2 because we factored out a 4. Cool so far? Okay, so now here we go. We're going to have to do integration by parts, right? So I'll choose another color here, all kinds of fun colors. We need to find the integral of negative t e to the t dt. So you would let u equal to t, du would equal to dt, dv is equal to e to the t dt, so v equals e to the t. I'm going to factor out the negative. We'll have u times v will be t e to the t, and then minus the integral of v du. So we have e to the t dt. So this is our little scratch work. That's going to equal to negative t e to the t plus e to the t. And we don't need our constant of integration for this one. Good so far? All right, so now we need also the other integral, right? So we're gonna need the integral of t e to the negative t. So if I have u equal to t, du equals dt, and then dv would be equal to e to the negative t dt, and v would be negative e to the negative t. So then we would have uv, so negative t e to the negative t, minus, it'll be minus a minus, right? So plus the integral of e to the negative t dt. That's going to give us negative t e to the negative t minus e to the negative t. Cool so far? All right. So now we've found this portion right here. So let's put that vector out there, and now we're going to need to multiply that one to phi at t. So here we go. xp will equal to negative 2 times phi at t. Phi at t we had way back here, right? Where was it? All right, e to the negative t, e to the t going across. And then 3e to the negative t, and then e to the t. We're going to multiply this to our result we found over here. So this is going to be, the first one was negative, I'll write it in the colors I did it in, I think. Negative te to the t plus e to the t. And then the second one was negative te to the negative t minus e to the negative t. And then xp is going to be negative 2 times. We're going to get, we have a 2 by 2, and we have a 2 by 1. So the multiplication is defined. We're going to end up with a 2 by 1. So this one, I'll write it out. We'll have e to the negative t times negative t e to the t plus e to the t. And then plus e to the t times the blue one, negative t e to the negative t minus e to the negative t. And then for the second entry below, we'll have 3e to the negative t times quantity, negative t e to the t plus e to the t, and then plus e to the t times negative t e to the negative t minus e to the negative t. Continuing the multiplication, we'll have negative 2 times. So notice that multiplying through the first one, the e to the negative t, all the e's will go away. So we're going to end up with negative t plus 1. And then for the second portion, again, the e's will go away, and then we'll have another minus t, and this time we'll have a minus 1. Going to the second one, we'll have negative 3t plus 3, and then minus t minus 1. Okay, so xp will be equal to negative 2 times. We'll have a negative 2t, and then the ones will zero out in the top entry. The bottom entry will have negative 4t plus 2. I'm going to bring the 2 in, so we'll have xp is going to be 4t and 8t plus, or 8t minus 4. And then the one way we can write this is we can write this as xp equals 4 and 8 times t, and then minus 0 and 4. Groovy? All right, so the last step is just to put it all together, right? So step 3, find x equal xc plus xp. So for this one, we just put it all together. So x equals, so our xc had been c1 times, where was that? 1, 3 e to the negative t plus c2 times 1, 1 e to the t. And then we put in what we just found for xp, plus 4, 8 times t, and then minus 0, 4. And we're all done. Isn't that awesome? I love these problems. It makes me weird. I think it definitely makes me weird. All right. Cool. I know it took a while, but I bet you feel great at the end of that one, right? Okay, so notice that we had this one more in kind of an equation form. This next one is going to be similar. It's just already given in x prime equals ax plus f of t. So it's a little, it might be easier to work with. So if you want to pause the video and try it on your own and then check your work, you can. Otherwise, I'm just going to cruise along and do this one, and we will, you do you. All right, so our A is here, right? So it's our 0, 2, negative 1, 3. F at t is, I'll just keep it all together, 2 and then e to the negative 3t. And remember, step 1, we need to find xc. And that meant the whole eigenvalues and eigenvectors business, blah, blah, blah. So let's do it. We need to find the determinant of A minus lambda I. Again, I in this case is I2, which is 1, 0, 0, 1. And so our determinant will be equal to negative lambda, 0 minus lambda, and then 2, negative 1, and 3 minus lambda. Now we'll set that determinant equal to 0, because that's what we'll be solving to find the eigenvalues. And so we'll have negative 3 lambda plus lambda squared minus negative 2. So 0 will be lambda squared minus 3 lambdas plus 2, which we are able to factor as lambda minus 2 lambda minus 1 times lambda minus 1. So lambda 1 will equal to 2 and lambda 2 will equal to 1. By the way, it doesn't matter which one you find first. I'm sure that's a question that might be burning in your mind. You'll get, you'll just have your C1 and C2, the matrices with the C1 and the C2 will be switched. So don't worry about it. Okay, so keeping it going, we have eigenvalues found, right? Then eigenvectors. Did I write that? Eigenvalues, all of this other stuff were eigenvectors. Alrighty, so eigenvectors, we need to find for lambda 1 equal to 2. We need to find A minus lambda I equal to the 0 vector. So that's going to be, for lambda 1 equal to 2, we'll get negative 2, 2, negative 1, 3 minus 2 is 1. I'm looking at the inside of the determinant. That tells me that's how I'm doing it so fast. And then we need to put in our zeros so that we can solve that system. All right, so if you multiply the first equation by negative 1/2 and then you add, you'll zero out that bottom line. So you'll have negative 2, 2, and 0, and then 0, 0, 0. And then if you further simplify by multiplying by a half to that top line, you'll have negative 1, 1, 0, and then 0, 0, 0. So if you put that into an equation form, you'd have negative 1k1 plus 1k2 is 0. And so k1 is going to equal to k2. If we let k1 equal 1, that would equal to k2. And so your eigenvector, first eigenvector, call it capital K1, would just be 1, 1. But your first x would be C1 times that eigenvector, and then times e. Our lambda was 2, so it'll be e to the 2t. Cool, cool? All right, next, these are eigenvectors. All right, so our next eigenvector, again, we have lambda 2 equal to 1. So we will have a minus lambda I equal to the 0 vector is going to give us, let's see, lambda is 1, so we'd get negative 1, 2 going across, negative 1. Now 3 minus 1 is 2. And then we have our dividing line, and we put our zeros. That's going to be equivalent to, they're the same, right? So the bottom line will zero out, and then you'll have negative 1, 2, and 0. And so negative k1 plus 2k2 is 0. 2k2 is k1. All right, so if we I'm going to let k2 equal to 1, that gives us k1 is going to be 2. And so capital K2, that vector, our eigenvector, is going to be 2, 1. And then capital X2 is going to be C2 times the vector 2, 1 times e. What was our eigenvalue? Was 1, so times e to the t. So here we go, we found xc. xc is equal to c1 times 1, 1 e to the 2t plus c2 times 2, 1 e to the t. Cool, cool? Okay, step 2. Find xp. And remember, xp was equal to phi at t times the integral of phi inverse at t times capital F at t, which we have from given in the problem. So if we kind of split this up a bit, first we'll find phi at t. So phi at t is equal to, if you just let c1 equal c2 equal to 1 and bring those exponentials in and make one happy matrix, we'll have e to the 2t, e to the 2t in the first column. Second column, we're going to have 2 e to the t and e to the t. So now phi inverse at t will be 1 over, I'm using that one method again, so we'll have e to the 2t times e to the t minus 2e to the t times e to the 2t. And then our matrix, we switch the main diagonals, And then we put the opposite sign in front of the coefficient of the other ones. All right. So our phi inverse at t will be equal to, so e to the 2t times e to the t will be e to the 3t. So we have 1 e to the 3t minus 2 e to the 3t is going to be negative 1 over e to the 3t, which is negative e to the negative 3t, times what we got in here. Bringing in the negative e to the negative 3t, we will end up getting phi inverse at t is e to the negative 2t, and then and that's a negative, sorry, and then a positive 2e to the negative 2t, a positive e to the negative t, and a negative e to the negative t. Now f at t, remember, was up here. So if we go ahead and find the product, because remember we need this product inside, so we'll find that now. So phi inverse at t times f at t equals, phi inverse was negative e to the negative 2t, 2e to the negative 2t, e to the negative t, negative e to the negative t, and then capital F at t was 2, and then e to the negative 3t. All right, we're going to end up with, we have a 2 by 2 and a 2 by 1, so we'll end up with a 2 by 1. So this is going to be negative 2e to the negative 2t plus 2e to the negative 5t, and then 2e to the negative t minus e to the negative 4t. And remember, this is what needs to be integrated, right? So we can pull that off to the side and take a look. So the integral of the first entry, we have negative 2e to the negative 2t plus 2e to the negative 5t. Integrating that with respect to t is just going to be negative 2e to the negative 2t divided by negative 2, and then plus 2e to the negative 5t divided by negative 5. That gives us e to the negative 2t minus 2/5 e to the negative 5t. Finding the second one, we'll have 2e to the negative t minus e to the negative 4t dt equals 2e to the negative t divided by negative 1 minus e to the negative 4t divided by negative 4, which will give us negative 2e to the negative t plus 1/4 e to the negative 4t. And so we're almost there. We now have that product. So remember that x at p was equal to phi at t times the integral of phi inverse at t times capital F at t dt. And so x at p, or x sub p, will be phi at t, which was up here, e to the 2t, 2e to the t, and e to the 2t. Now, the integral, the second part here, all of this is going to be what we found in these integrals. And so that's going to be I'm going to write it in the same color. So to the integrals, e to the negative 2t minus 2/5 e to the negative 5t. And then the green one was negative 2e to the negative t plus 1/4 e to the negative 4t. All right, and now we multiply. So xp will be equal to, it's a little more complicated of a multiplication, so I'll write more steps. E to the 2t times the quantity, e to the negative 2t minus 2/5 e to the negative 5t, and then plus 2e to the t times the quantity, the green part, negative 2e to the negative t plus 1/4 e to the negative 4t. And then the next entry will be e to the 2t times e to the negative 2t minus 2/5 e to the negative 5t plus e to the t times negative 2e to the negative t plus 1/4 e to the negative 4t. Simplifying, we will have 1 minus 2/5, and that'll end up being e to the negative 3t, and then minus 4 plus 1/2 e to the negative 3t, and then we'll have for the bottom one, I'm going to make those longer. E to the 2t times e to the negative 2t is 1 minus 2/5 e to the negative 3t. And then minus 2 plus 1/4 e to the negative 3t. Simplifying, we have, I'm going to put the t term first. We have a negative 2/5 e to the negative 3t and a positive 1/2. So their common denominator is 10. And so we'd have negative 4/10 plus 5/10 is positive 1/10 e to the negative 3t minus 3. Same with the bottom, except the common denominator is 20. So we'd have negative 8/20 plus 5/20. So we'll get negative 3/20 e to the negative 3t minus 1. And so we could write xp if we wanted. You could keep it like that, or you could separate it and you could write it as 1/10 negative 3/20 e to the negative 3t minus 3/1. Cool, cool? All right, now, last step, my friends. Put it all together. So x equals xc, let's find all this, remember from here. That was messy. This was xc here. So xc, c1, 1, 1, e to the 2t. Plus c2, I think it was 2, 1. Yep, e to the t. And then plus 1/10 negative 3/20 times e to the negative 3t minus 3 and 1. And that's it. And we're all done. All right. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, go ahead and subscribe, share, and hit that like button. Thank you.